Hello friends, welcome you all to the 50th lecture on functional analysis and its applications. In this lecture, we will discuss the unitary operators on Hilbert spaces. Content of today's lecture is unitary operators on Hilbert spaces. Definition of unitary operators. An operator T on a Hilbert space H is said to be unitary if Tt star equal to T star T equal to identity operator, where T star is the adjoint of T. From the definition, we note that if T is unitary, then it is normal. This is the definition of normal operator. Tt star is equal to T star T. It means we can say that unitary operator is a normal operator. Also, T star equal to T inverse, that is adjoint of T is denoted as T inverse when T is unitary. Theorem: if T is an operator on a Hilbert space H, then the following conditions are equivalent to one another. First, T star T equal to identity. Second, inner product of Tx and Ty equal to inner product of x and y for all xy belonging to H. And third, norm Tx is equal to norm of x for all x belonging to H. Let us prove it. We have to prove all these three conditions are equivalent. So we will prove if one is given, then second is true, and second is given, then third is true, and third is given, then first is true. So we can say that all three conditions are equivalent. So suppose first is given T star T is equal to I. So if T star is the adjoint of T, we have by first T star T is equal to I. So inner product of Tx and Ty can be written as inner product of x T star Ty. Okay, as per the definition of adjoint operator, because we know that inner product of Txy equal to x T star y. So this T can be operated on this with adjoint as per this definition. So inner product of Tx Ty can be written as inner product of x T star Ty. So T star T is equal to I given, then we can write this as inner product of x and identity operator of y. Identity of y, that is y. Hence, inner product of x Iy equal to inner product of xy. So second proved, inner product of Tx Ty equal to inner product of xy. Second to third. In second, we are given inner product of Tx Ty equal to inner product of xy. So we have to prove a norm of Tx is equal to norm of x. So if we take y is equal to x, then this one can be written as inner product of Tx equal to inner product of xx. And also we know that inner product of xx is norm x square. So this can also be written as norm of Tx square. So this implies that norm of Tx square is equal to norm x square. So taking square root of both sides, we get norm of Tx is equal to norm of x for all x belonging to H. So third proved here. Now we prove third to first. So by third, we have norm of Tx is equal to norm of x. So squaring both sides, we have norm of Tx square is equal to norm x square. So norm Tx square can be written as inner product of Txx, and norm x square can be written as inner product of xx. So this is inner product of Tx equal to inner product of xx. So as per the definition of adjoint operator, this can be written as inner product of T star Tx x equal to inner product of Ix x. X can be written as Ix. So taking these in left side. Okay. So this can be written as T star T x minus inner product of x equal to 0. Okay. So as per the additive property of inner product, this can be written as inner product of T star T minus I of x and x equal to 0. So also we know that if inner product of Tx x equal to 0, then T is 0 operator. So here T star T minus I H operator. So these x and x under inner product equal to 0. So T star T minus I is 0 operator. That is T star T minus I equal to O. So this is 0 operator. Hence we can write T star T is equal to I. Hence first condition also proved. Hence we can say that all these three conditions are equivalent. This completes the proof of the theorem. Next theorem. An operator T on a Hilbert space H is unitary if and only if it is an isomorphism of H onto itself. Proof. Let T be a unitary operator on H. Then from the definition of the unitary operator, it is invertible because here this, therefore it is onto. Further, Tt star is equal to I. Hence by the previous theorem, norm of Tx equal to norm of x for every x belonging to H. This proves that T is an isometric isomorphism of H onto itself. To prove the converse, let us assume that T is an isometric isomorphism of H onto itself. Then it is 1 to 1 and onto. Therefore, T inverse exists. From our assumption, norm Tx is equal to norm x for every x belonging to H. By theorem first, equation 1 implies that T star T is equal to I. Because from first here, norm Tx is equal to norm x, then T star T is equal to I. Okay. So here, given norm Tx is equal to norm x, then this implies that T star T is equal to I. Hence, post multiplying by T inverse, T star T into T inverse, that is T star T applying on T inverse. Okay. So T star T equal to I. So it can be written as I T inverse. Okay. So this implies that T star into TT inverse. That is T star applying on TT inverse. Meaning of this is this. Okay. And I T inverse, that is T inverse. Thus T star is equal to T inverse. Okay. Now pre-multiplying this T, we have TT star equal to TT inverse is equal to I. Similarly, post multiplying by T in equation 2, we have T star T equal to T inverse T. Okay. So T inverse T, that is I. Hence Tt star is equal to T star T equal to I, which proves that T is unitary operator. Next theorem. Prove that the set of all unitary operators on a Hilbert space H forms a group. An operator T on a Hilbert space is unitary if Tt star is equal to T star T equal to I. That is, T is invertible and T inverse equal to T star. We verify the axioms of group for the set of all unitary operators U on H. First, let T1 and T2 belonging to U. Then T1 and T2 are invertible and T1 inverse equal to T1 star and T2 inverse equal to T2 star. Since T1 and T2 are operators on H, T1 T2, that is T1 into T2 is also an operator on H, and since T1 and T2 invertible, then T1 T2 is also invertible. Now inverse of T1 T2, that is T2 inverse into T1 inverse, and T2 inverse is T2 star, T1 inverse is T1 star, that is star of T1 T2, because we know that star of T1 T2 is T2 star T1 star. So T1 T2 inverse, that is inverse of T1 T2 equal to star of T1 T2. This shows that T1 T2 belonging to U. Second, since the product of mapping is associative, the product is operators is also associative. That is, if T1, T2, T3 belonging to U, then we can write T1, T2, T3 equal to T1, T2, T3. This can be written as T1, T2, T3. That is associative. Let I be the identity operator on H. Since I is 1-to-1 and onto on H with norm Ix is equal to norm X. So here I is unitary operator, and unitary operator can be written as star of unitary operator is equal to inverse of unitary operator. That is I star is equal to I inverse, because here I is unitary. Fourth, if T belonging to U, we show that T inverse belonging to U. From the definition of unitary, T inverse is equal to T star. Note that T inverse is an operator and T inverse is also invertible. Hence, inverse of T inverse, that is star of T inverse, that is adjoint of T inverse. Because we know that if T is unitary, that is T inverse is equal to T star. So here T also invertible and this is an operator. So this can be written as inverse of T inverse is equal to star of T inverse, which proves that T inverse is unitary. Hence, U is a group under the composition of operators. Noting point, if T is an unitary operator on H, then norm T is equal to 1. For unitary operator, we have norm Tx is equal to norm X. So that norm T is equal to supremum of norm Tx upon norm X, where norm X not equal to 0. Okay? So, if T is unitary, then norm Tx is equal to norm X. So, here norm Tx is equal to norm X, hence norm T is equal to supremum of norm X upon norm X, that is 1. Okay? So, if T is unitary, then norm T is equal to 1. Next definition. Let S and T be linear operators on H. The operator S is said to be unitarily equivalent to T if there exists a unitary operator U on H such that S is equal to UT U inverse. Since U is unitary, so U inverse is equal to U star. Okay? So that S is equal to UT U star. This can be written as S is equal to UT U star, because U inverse is U star. Theorem. If T is self-adjoint, any operator S unitarily equivalent to T is also self-adjoint. Okay? Since S and T are unitarily equivalent, we have a unitary operator U on H such that S is equal to UT U inverse as per the definition. Okay? So, U is unitary operator, that is UT U star. Using the properties of adjoint operation, S star is equal to star of UT U star. Okay? So, this can be written as U double star T star U star, because we know that T1 T2 star equal to T2 star T1 star. Okay? So, this can be written as, suppose this is UT U star. So, this can be written as U double star UT star, and this can be written as, this is double star U double star and this T star U star. Okay, that is this one. And also we know that T double star is equal to T. So, U double star can be written as U, T star, U star. So, U is unitary operator equal to U, T star, U. Here T is self-adjoint, then this can be written as U, T, U star. So, again we have U, T, U star, that is S. So, S star is equal to S. This proves that S is self-adjoint. Example of unitary operator. let T such that L2 to L2 be defined. TFT is equal to FT for T greater or equal to 0 and minus FT for T less than 0. Then T is unitary. Solution. Here clearly T is linear. So I am avoiding here to prove T is linear. And inner product of T star TFG. As per the definition of adjoint operator, this can be written as inner product of TFTG equal to integral minus infinity to infinity TF and conjugate complex of TG dt. This is by the definition of the inner product of L2. Here TFT defined in two ways, for T greater or equal to 0 and T less than 0. So we break this integral in two terms. Integral minus infinity to 0 plus 0 to infinity. So minus infinity to 0, if T less than 0, that is minus Ft. Value of TFT is minus Ft. So here minus infinity to 0 minus F minus G bar, because value of Tg is minus G when T less or equal to 0, plus integral 0 to infinity F into G bar dt, because function here defined for T greater or equal to 0 is Ft. So here integral 0 to infinity, so value of Tf is F and value of Tg is G. So here minus and minus, that is plus. So integral minus infinity to 0 F into G bar dt plus 0 to infinity F into G bar dt. Hence this integral can be written as minus infinity to infinity F into G bar dt. Hence this can be written as inner product of Fg as per the definition of inner product in L2. Okay. So this can be written as inner product of IF and G. So here inner product of T star TFG equal to inner product of IFG. Hence T star TF is equal to IF. That is T star T is equal to I. Thus T is unitary operator. In this lecture, we have discussed the unitary operator and its properties. These are the references which have been used in this lecture. Function analysis, Dover publications written by George Beckman and Lawrence Nursi. Second, introductory function analysis with applications, John Whaley and Sons written by Erwin Krejcik. Third, function analysis, New Age International Publishers written by V.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill written by Waterwoodin. Thank you.